The aim of this lab was to examine the motion of a stretched slinky that has a tennis ball attached to the bottom. As the top of the slinky is dropped from static equilibrium, as seen in the video, slinky drop extended by Veritasium. We will use Tracker to extract the position data of the top of the slinky and of the tennis ball in the video, only considering movement in the y direction as time advanced. Then we will construct a computational model of the motion in VPython. We will compare the predicted and the observed motion and discuss why the slinky and ball moved in this way. We found that the top section of the slinky collapses turn by turn from the top. Each coil doesn't move until the one above it comes down and nearly hits it. The acceleration of the top of the slinky was initially faster than the gravitational field strength. The ball attached to the bottom of the slinky stays stationary, just like in the video. The ball begins to fall when the top section of the slinky collides with it, whereupon the now collapsed slinky and ball fall together as a single mass. The observed total collapse time of 0.24 seconds corresponds to the time required for the wave to propagate down the slinky to communicate the release of the top end. First, we obtained position data from the video using Tracker. If you would like to see the video, the link to it will be below. The origin was set at the initial position of the top of the spring, with the rest of the spring and the tennis ball hanging in the negative y direction. The measurements were calibrated to the diameter of an average tennis ball, which is 0.065 meters. I tracked the point masses for the position of the top of the spring, and in the frames that this was blurred, I marked the center of the blur as an estimate of the position. I then did the same for the tennis ball, marking its center as the best estimate of its position. This is the model. Observations from the video provided the initial conditions of the ball and slinky, so their initial position and velocities. We know that at the start of the video, the slinky and ball are at rest, so their initial velocity is 0. The mass of the objects is included in standard SI units of kilograms. Delta t, so the change in time, was set to be 1 over 300 seconds, as this time interval was much smaller than the timescale of the motion observed. I specified the constant g to describe the strength of the gravitational field, and I put in values for the spring stiffness k sub s and the spring's relaxed length L0. The L vector gives both the length and orientation of the spring. In this code, the variable spring.pause is the location of the top of the spring. The unit vector L hat describes the direction of the L vector. S describes the stretch or compression of the spring. We got the time of the last observation from Tracker. Newton's second law is used repeatedly in this loop to predict the velocity and the position of the objects as time advances. I modeled the drag force as being in the direction opposite to the object's motion, and with a magnitude proportional to the square of the object's speed. B is the proportionality constant in Newton seconds per meter. We know that the spring force is equal to the spring stiffness K sub S times S, which is the difference between the actual length of the spring and its relaxed length. The negative sign indicates the direction that the spring stretches is opposite to the direction of the force which the spring exerts. The weight force on the system, caused by the gravitational pull of the Earth, is equal to the mass of the objects times the gravitational field strength. F gravity acts only in the y direction, so that is why its x and z components are 0. The system, which in this case we took to be the ball and the spring, was affected by two forces from the surroundings, the weight due to the gravitational force from the Earth and the drag force. The slinky also provided a spring force. Therefore, we have set the net forces on the ball and slinky as being equal to the sum of these forces. These lines of code update the spring force, and this line updates the visualization of the spring. Now we run the program. The blue arrow represents the spring force, and the black arrow represents the weight force. We see that the weight force in black always points down and does not change in magnitude. The blue arrow representing the spring force gets shorter as the top of the spring falls, because the spring force decreases. The model does appear to show the same kind of motion as observed in the video. However, the model does not predict the motion of the falling spring in the video directly, because it did not know the actual weight and size of the spring and ball used, so I had to just use average values. Also, in the real observations, once the top section of the slinky collides with the ball at the bottom, the now collapsed slinky and ball fall together as a single mass. However, in my model, the spring just passes through the ball as though it were hollow. So what does it mean? Why does the motion actually look like this? This graph shows the motion of the ball which is attached to the bottom of the slinky as time advances. We can see that initially there is some very little movement of the ball. When analyzing the data in Tracker, in some frames the objects were blurred, so I might not have been able to pick the exact position of the ball. This could explain what we are seeing here. In the video, it does look as though the ball moves slightly when the top of the spring is falling towards it, but this is only because the man holding the slinky did not wait for it to stop moving entirely before dropping it, so the system was not completely in static equilibrium. This second graph allows us to compare the position of the top of the slinky in red and the ball at the bottom of the slinky in blue. We can see that the top of the slinky falls very quickly and the effect of drag seems negligible. We can also see that the ball remains pretty much in the same position until the top of the slinky reaches it. These diagrams show the forces on the top and the bottom of the slinky. For such a short fall, we may assume that the air resistance was negligible, and in the absence of drag, we know that the speed of a falling object increases at a steady rate, and all objects, irrespective of their mass, have the same acceleration of freefall. The center of mass for the stretched slinky and ball system, just like any other falling object, accelerates downwards at g, approximately 9.8 meters per second squared. Parts of the multiparticle system accelerating with respect to the center of mass may accelerate faster or slower than g. The top of the slinky begins stationary, with the forces acting on it being balanced. However, when it is released, gravity and the stretch of the slinky pull it down, therefore it accelerates down faster than the acceleration of gravity. The ball attached to the bottom of the slinky initially is just hanging motionless, which means that it is in static equilibrium. Therefore, the gravitational force and the spring force acting on it are equal and opposite. When the slinky is released, the upward spring force remains the same, so the ball at the bottom of the slinky just stays stationary. We can sum this up by saying that, at the same time as the center of mass is accelerating downward, the top and the bottom of the slinky accelerate towards the center of mass of the system as the slinky is compressing to its relaxed length. If you release the top of the slinky, it takes some time for the wave to travel down the length of the slinky and change the tension at the bottom. Note that the center of mass of the slinky and ball system is not at the center of the slinky, because the slinks at the top are stretched far apart, while the bottom ones are much closer, and the ball adds additional weight to the bottom. What if? If there was more weight attached to the bottom of the slinky, it would still behave the same way. However, the initial stretch before release would be longer. Hooke's law states that the extension of the spring is directly proportional to the force applied to it, as long as the elastic limit is not exceeded. If too much weight was applied to the bottom of the slinky, which caused it to be stretched too much, it would not return to its original length when the mass was removed. Then it would not behave the same way when falling. Thank you very much for watching.